First thing I want to talk about is this agentive coding project that I've been working on. So this is actually a paper based on the stuff that I was originally planning to do for embodied intelligence. And this was not the thing that I presented at Embodied Intelligence this year. There was a different talk, which is actually quite interesting, and it's on our YouTube channel, called Embodied Models from the 80s. If you saw that video, it was, pretty nice. It's just basically all of the sort of underpinnings of what we think of now as like embodied agents and things like that, and just kind of the origins of it.
I'm sure that's been covered here in one of our meetings recently too.
Because
if not, I'd love to just go over that. Yeah, because I haven't been able to be here and I haven't read that video fully, but like the title and the styling and everything, it was very cool and super appropriate too. And that's something that I, I'll save it for other time. We can go on this, but like, yeah. So I'm one question I was just about to type too. I see you put this on preprints.org. Do you like preprint.org for this kind of thing?
I mean, it's just kind of like I don't think it would go on archive or bioarchive, and then I usually use archive, bioarchive, OSF, or this. So like OSF is usually like psychologically oriented papers or some of those things. This is just kind of different, so I wanted to use a different preprint server.
Okay.
Sometimes they don't, like archive and bioarchive don't accept certain types of papers. So
right.
Anyways, I'm using this. Yeah, I'm using this different preprint server for this. In any case, so yeah, that talk, embodied models from the 80s, it kind of fits this because it kind of frames like, you have a bunch of approaches that kind of come out in the 1980s and early 90s. And those approaches kind of inform what we're doing today. And so what I'm doing here is I'm kind of synthesizing a bunch of things that are going on in our world today of, different types of machine learning models, different types of computational models, and putting them together to sort of solve this problem. So the problem is that I want to build agent architectures that are embodied, but also have this sort of, these mixed properties. So if we think about like something that's specialized, if we were to specialize an architecture, say, for spatial cognition, we might hand code this or design this in a way that is specialized for spatial cognition, and that would be the function. And our conception of function is limited by our ability to think of what the function should be that we want. So in other words, it's extremely goal oriented. We kind of have this series of tests. It performs well on a benchmark, and then that's our architecture. But in this case, what I want to do is I want to do two things. I want to evolve architectures for, maybe certain task settings. And when you evolve an architecture, of course, you can make it more sort of adaptive to the general sort of way of doing spatial cognition as opposed to, optimizing it for a specific task. So you have robustness, you have these other properties that we associate with, a complex system solution. But then on the other hand, I wanted to take different lineages of these genetic algorithms. I wanted to mix them together into different meta architectures. So like for things like metacognition or multifunctional agents or things like that. So this approach, phylogenetic mixing, is kind of what I wanted to highlight. And what I did here is I used a combination of two agents. Well, actually, mostly Copilot, but then I also used a little bit of Notebook LM and the Gemini model as well. But in any case, I used agentive programming to build the models and to specialize them for this purpose. And so what I ended up doing is I ended up creating this pipeline for going from some sort of generative data set to like a selection mechanism, a genetic algorithm where I had selection, and then that would produce these evolutionary lineages of agent designs. And then I would find I would select the best ones, and then I built this framework for sort of putting those together, which was based on hypergraphs. So this is kind of going over the methods that I basically used to do. So this was all a proof of concept. I didn't actually build the agents, but I wanted to go through kind of the way in this pipeline would work. So, ideally you might give this feed data into this pipeline that define different neural architectures. Like we talked about last week, we talked about neuroecological architectures. And you might come up with those kinds of architectures and feed the components of those architectures into this pipeline. And so what I did was I modeled this with very simple shapes. And I also built part of the pipeline with a Bratenberg vehicle data set that I already had, which was basically where I built these different Bratenberg vehicles out of their components. And so this is an example, the shape data set. So it was like you had squares, circles, and triangles. Those kind of represented body parts. And then this was fed. So I have figure 1 here. If I can get to figure 1 here. So what I did was I fed this. I actually did the training in 2 ways. The first way is that I fed the shapes data set into the reservoir network that I defined. And then I fed this into a forward diffusion process, which was an alternate approach to this. So I had the reservoir network, the diffusion process, and I generated a bunch of combinations. So, and then I found the connections between them. So this was kind of building this network that was then we used, or I used the GAN which is a generative adversarial network. So the GAN would actually build the weight. Well, we'd get like this, basically this quasi-latent space from both the reservoir network and the forward diffusion process. And then the GAN would be used to generate the latent space and then find interesting connections within the latent space. So you would, in the reservoir network and diffusion process, you'd generate all these shapes, or you'd have these shapes and you'd train the model to find the patterns or the connections in that model. So you'd find similar types of squares, similar types of circles, similar types of triangles. And then with the GAN model, you would produce candidate latents for the latent space. So you'd construct the latent space, you'd map it to a metric space, and then you would generate shapes and other things that would be done with the discriminator. With the diffusion process, there was also this reverse diffusion step, which sort of produced the same approach. So, this is all basically taking this data set, creating a sort of a network of similarity, creating a latent space to select from, and then selecting from that latent space. And then the final step was to take that output and to apply a genetic algorithm that applied a fitness or a selection criterion. And so there were 2 selection criteria. One was for sort of similarity, or what was called sort of lineage specific relationships, and then another one which was a creative criterion, which sort of was analogous to convergent evolution, or when 2 lineages produce 2 different solutions for a similar function, like bird wings and insect wings, that sort of thing. So this was the pipeline, and it worked it out. And then I also had the Bratenberg vehicle data set, which was something that was also generated in a similar way. So these are some examples from the reservoir network based on the Bratenberg vehicles data set, where you had this body and then this internal model, which was a circle. These are just basically experiments to sort of get this ball rolling. They kind of figure out how this should work, and then eventually, this could be used for building more complex architectures that actually do things in the world. So I wanted to but I did want to demonstrate embodiment here. So then, these are the technical details still. And this is kind of the way this worked. So you would have these shapes that were generated in this space, and then this is sort of the output of a reservoir network, I believe. And then you would have this selection mechanism that resulted in this bottom graph. So this is the product of the GAN versus the GA model. And so you see that this is kind of clustered in one part. These shapes are clustered in one part of the latent space. Is also representing only triangles. It's selecting for triangles. So this is another example here. And then this output, which is the product of a GAN versus and a GA combined, produced this evolutionary tree. So it was able to produce evolutionary trees from the selected data, basically their relationship, either based on novelty or similarity. And then, of course, this is mapped to hypergraphs where you're taking these different nodes and you're putting them into these collections of graphs within graphs, and then you're able to take that ensemble and apply it as a complex architecture. And so there are different ways you can do hypergraphs. You can do something like this, which is a nested hypergraph, or you can do a bipartite hypergraph, and this is based on the Bradenburg vehicle data set, which relates different aspects of the Bradenburg vehicle to these specific vehicle designs as featured in Bradenburg's book. The Bradenburg vehicle data set was interesting because I could break the Bradenburg vehicle down into its component parts. But in Bradenburg's book, he also gives information about the specific vehicle designs and about the behaviors. As you know, they weren't precise in the sense that they were tested. He just kind of generated, this was a thought experiment on his part. So he was generating these behaviors and these designs. And so that you can use this to kind of explore what's actually going on in that paradigm, which is very interesting because I think people have used Bradenburg vehicles in the sense of kind of building them into robots, but I don't think people have ever analyzed sort of the way in which Bradenburg vehicles, the whole premise of Bradenburg vehicles are presented, and the sort of the details in those descriptions. So, this is a good way, to kind of decouple but also connect at a higher level, like morphology and sort of the architecture with the behaviors, with the function. Okay, so that was a little bit, and then this is a model of addressable phylogenies in Bradenburg vehicles. So, this is kind of bringing this idea together into a higher order representation where you have these vehicles that have been decomposed in terms of their parts and then reassembled using this process. And then you can build a representation that allows you to evolve these reconstituted architectures.